just like continuing on glycolysis, linking glycolysis to the citric cycle is the oxidation of pyruvates. The oxidation of pyruvates happens within the mitochondrion for eukaryotic cells, for prokaryotic cells in the cytosol. What can we say about the oxidation of pyruvates? Just few ideas. The pyruvates actively enters the mitochondrion, and it will form the acetyl coenzyme A. Now, the acetyl coenzyme A, the oxidation of pyruvates in order to form the acetyl coenzyme A will release CO2. That's one. And we can just look at it here, the 3 steps of oxidation of pyruvates. The pyruvates carboxyl group, okay, it's already oxidized. It has already lost H. There's no H. It will be completely oxidized and released as CO2. That's the first release of carbon dioxide in cellular respiration. Second, so now we have 2 carbon groups, a 2 carbon fragment, let's call it, is further oxidized, and this oxidation will provide us with NAD+. That's also the only energy providing aspect of pyruvate oxidation. And the third step is the formation of acetyl coenzyme A that will be the molecule from glycolysis and then pyruvate oxidation to enter the citric cycle. Coenzyme A, it's a sulfur containing group made from B vitamin, will attach to the acetyl group. Now, to remember, acetyl group is I think C something. Oh, it's a 2 carbon fragment that we obtain from 2 oxidation steps. The first is the complete oxidation of CO minus, releasing our first CO2, and the second, which is the providing NAD plus with electrons and 2H. Once we acquire acetyl coenzyme A, from coenzyme A, the sulfur compound made from B vitamin, we are ready to start the citric cycle. That's all of it. Now, this is a couple of ideas to grab from the text regarding the citric cycle. One idea is that for the first 5 steps of the cycle, we are able to tag or follow. Let's call it let's call it survey. I don't know what to call it, but let's call it that we will be able to locate each carbon, its location, and what is released. That's as the pyruvate is broken down. The pyruvate has 3 carbon. It's a 3 carbon structure. It has 3 carbons. The first is released in its oxidation prior the attachment to coenzyme A. So now we have 2 carbon atoms. They're marked in red in the cycle. Once it attaches, once it becomes part of the coenzyme A, entering the cycle, it will connect. It will react with oxaloacetate and forms citric acid. It's the citrate. Citrate has 4 carbon atoms, and if it has multiple atoms, but we have 4 carbons highlighted red. They will remain in the cycle. Blue will leave the cycle. All of them can be tracked up to the formation of up to the formation of succinate, as in succinyl coenzyme. Then the 5th step, like half the cycle, let's say more than half. At the 5th step, this is a very unique step. This is a unique step because it provides us with the only ATP or GDP, and it will produce succinate. We can no longer track the acetyl carbons, the 2 carbons from acetyl coenzyme A, because succinate is symmetrical. That's the idea here. Is that I think that it's mentioned somewhere here that since we can't track these carbons because succinate as a molecule is symmetrical, we cannot say for a fact that these carbons became part of oxaloacetate or something else. But what we do know for a fact is that these carbons, they do not leave the cycle together at the same time. One might remain and take part of different parts of the cycle, and another can leave, and we can't tell for sure because both of them are part of a symmetrical molecule, that is the succinate. Anything else? The tally, of course, the tally. Now, it has an 8-step. It's an 8-step cycle. They've explained the molecules in the blue and the red. What makes it a cycle is that once citrate is formed by combining acetyl coenzyme A with oxaloacetate, oxaloacetate will be reobtained at the end of the cycle, and acetyl coenzyme A will continue to be provided from outside the cycle, and that's why it is a cycle. Okay. Bear in mind, first 2 steps are just making citrate. 3rd, 4th, they produce CO2, and they will reduce NAD to NADH. Eighth step will produce NADH, but it's the only one from the three that doesn't produce CO2. Fifth step is the only step that provides substrate level phosphorylation of ADP or GDP, and it's the only direct source of ATP in the cycle. The sixth step provides two electrons, two hydrogen atoms to FAD, which is flavine, adenine dinucleotide. Done. The tally in general. Now remember that we have two pyruvates from glycolysis. Both will be oxidized. Both will provide acetyl coenzyme A. Each glucose will provide two acetyl coenzyme A. One will enter the cycle, and for each acetyl coenzyme A entering the cycle, we have 3 NADs reduced to NADH, step 3, 4 with CO2, 8th without CO2. We have 1 ATP or GTP, phosphorylated, substrate level phosphorylated and produced. We have 1 FAD that is reduced per acetyl coenzyme A. Per glucose, per 1 glucose, we have double that. That is 6 NADs reduced, 2 FADs reduced, and 2 GTP or ATP. And okay, in here, one information is important. All enzymes in the cycle are present in the mitochondrial matrix, except one, which is at the 6th step, which is a unique step because it's the only step where FAD is reduced. And the enzyme that catalyzes that step, that special step, exists in the inner mitochondrial membrane. Looking at the cycle, the beginning, we have the acetyl coenzyme A made from oxidized pyruvate that will provide us with the acetyl, and coenzyme A that comes from vitamin, derivative of vitamin B. The first 2 steps are just making citrate. What makes this a cycle is that oxaloacetate will always be present here, to combine with acetyl coenzyme A in order to produce the namesake citrate, citric cycle. So we have the coenzyme A, the acetyl coenzyme A complex. It will react with oxaloacetate, providing us with citrate and releasing the coenzyme SH. As an coenzyme A reduced, having an H that will serve in the 4th step. Then O2 will exit and re-enter to rearrange citric acid, citrate into isocitrate. The 3rd and 4th step, they have what they have in common is that the substrate in the cycle will be reduced in each, and both will produce CO2, and both will reduce NAD plus 2 NADH. The fourth step, the substrate from isocitrate will become ketoglutarate. Okay, doesn't matter. The same thing happened. CO2, NAD reduced, H plus, H plus. Now we are still able to track the carbon atoms, the red that were marked to be part of the acetyl coenzyme A. There's now part of citrate, isocitrate, the first atom, and two blue atoms that were tracked as part of oxaloacetate. So now we know for sure that the blue atoms, the blue carbons that came from oxaloacetate will be ejected as CO2. Up till the succinyl coenzyme A, which is after the fourth step, we no longer have blue carbons. They became part of the CO2, and the carbons from the acetyl coenzyme A, they're still present, they're still tracked. However, once the fifth step, once this substrate goes through the fifth step, which is a remarkable step, like it's a unique step, because it's the only step at almost half the cycle, the only step that produces GTP and ATP by first by attaching the phosphate group, the inorganic phosphate group, to succinyl coenzyme, removing the coenzyme and taking its place. Then it will substrate level phosphorylate GDP or ADP, producing our only direct source of TP. That will cause a change in the molecule. The succinyl will become succinate. Succinate is an asymmetrical compound substrate. We are unable to track the carbons. We will not be able to know which carbon will proceed with the rest of the cycle, and succinate will be oxidized, and we have two specific characteristics of the sixth step. First, we remember that it's the only step where the enzyme isn't in the mitochondrial matrix, it's in the inner membrane. Second, it's the only step that reduces FAD plus 2 FAD H2, and doing so, succinate will be oxidized into fumarate. Fumarate will change its form, rearrange the bonds using water into malate, and malate in the seventh step, in the eighth step, will reduce NAD plus into NADH without ejecting CO2, as opposed to the third and fourth step. And now, after the malate is oxidized, it becomes oxaloacetate, and the cycle will continue.